Alright, so let's take a look at what a normal distribution is all about. And the reason that I've come over to the document camera for this is that I'm going to draw some pictures, and so it'll be helpful for me to be able to actually draw them. Alright, so the characteristics of a normal distribution. And specifically, I'm going to list 3 characteristics here. The first one is that it's symmetrical. So you should have noticed on all the slides that I had before, we didn't have any skewed distributions there modeled with the bell curves. All of them were totally symmetrical. The second, and I've already been calling them bell curves, so this one should be pretty obvious, but the second characteristic is that they are bell-shaped. And these are going to be qualities that are true of every normal distribution. The third one is that the area under the curve is going to be equal to 1. And so hopefully the reason that I went through this example up here is becoming a little bit more clear now. And it's because in the same way that you could add up the area in these bars to get 1, you can add up the area under the curve in a normal distribution to get 1 as well. And specifically, you can think of it kind of as like it's made up of lots and lots and lots of little teeny tiny bars. Each of them have an area, just like the bars up here did, and if you add them all up, it should equal 1. And again, the reason that the area under the curve in a probability distribution, or the area that's made up of all these little bars, equals 1 is that your probability distribution is telling you probabilities about things, and probabilities always add up to 1 when you're looking at one set of outcomes, because there's a 100% chance that something you're describing here is going to happen. All right, so how I'm going to be drawing these normal distributions in the class is typically going to be as a bell shape like this. We're going to have some sort of variable values or outcomes on the x-axis, and we're going to have probability modeled on the y-axis. And normal distributions also have another set of characteristics. One is that the mean of the distribution, which if you remember from last time we call mu, is always going to be at the center of the bell curve. So thinking about means for probability distributions, if you remember, the mean for the probability distribution tells you if you were to actually take a sample based off this probability distribution, what mean you would expect to get in that sample. So if you were to take a sample that was based off this probability distribution, so say this is Chipotle meals, and you're taking a sample of Chipotle meals, if the mean for your probability distribution is 1,000 calories, you would expect the mean of your sample of Chipotle meals to also be 1,000 calories. As you can tell, I've made myself hungry. Anyway, back to probability distributions. Another characteristic of probability distributions is that they have standard deviations. And this is, again, similar to the examples we had last week, where the standard deviation of your probability distribution tells you what standard deviation you would expect if you were to actually take a sample based off of that probability distribution. So whatever the standard deviation of your probability distribution is, it tells you what your sample would look like, so in other words, how spread out it's likely to be. And then, as one final point about these probability distributions, because we're thinking of them as teeny, teeny, tiny bars that all correspond to lots and lots of different values that you can have here, variables that are modeled by a normal distribution have to be continuous or close enough to it. So what I mean here by continuous variables, I mean variables where there are not big gaps in between the different values that you can have. So essentially they're variables that either are measured where you have values that are decimal places that are sort of in between each numerical value that you have, or where you have so many possible values that you could imagine them as being modeled by these teeny tiny little bars like this. So if you're thinking about something like number of calories, you could have something that's 1,000 calories, you could have something that's 1,005 calories, you could have something that's 1,005.2 calories. You could have something that's 1,005.2000001 calories. So basically, you have a variable that's continuous because there's no real breaking point. You can chop them into as small a decimal place as you want, and you could have a bar that corresponds to 1,000, 1,005, 1,005.2, and you would still have some probability there. So it's just some variable where the numbers that you can have on it are continuous. And as an example where you're close enough, you could think of something like test scores on the SAT. So with SAT scores, you're getting some number there. You can't necessarily get a fraction of a number on your SAT score, so you couldn't get like a 1,500.2, but when you have numbers ranging from 400 to 2,400, you have enough different values in there that you could imagine having little teeny tiny bars for each one. A variable where you couldn't have a normal distribution would be something like this, where you can't have 0.1 heads when you flip 2 coins, and you don't have enough variables that you can have little teeny tiny bars for each one. So instead of having a normal distribution here, we have this big blocky distribution that can only look like this. So with that, I'm going to hop back into the PowerPoint, and I'm going to talk about what normal distributions with different means and standard deviations look like.